Welcome back. This is the third part of a series of lectures wherein we introduce the mathematical conservation equations to model the porous electrodes. In the previous lecture, in this lecture, we introduced two conservation equations relating to the current densities in the solid phase of the porous electrode and the um, liquid phase of the porous electrode. So few important aspects have to be re-emphasized. One is there is one current density which is normalized to the superficial area, or we clarified what we mean by superficial area in the previous lecture. Please refer to that. And then there is another current density with respect to the actual interfacial area available between the electronic phase and the electrolytic phase. So the way to relate these two current densities are via this important quantity, which refers to the combined surface area. In a typical porous electrode, these surface elements are randomly oriented, but in this structure, we have these idealized cylindrical pores. So this quantity helps us relate these two current densities. So this is just a conservation equation, right? So this refers to a difference in a particular flux. This flux is normalized to superficial uh, surface area. And this term indicates a volumetric charge rate generation term. So this kind of conservation equation you must have seen in many transport related courses. We'll move on. We will look into few other conservation equations that helps us completely specify the relevant variables in the porous electrode. We have looked at the general materials balance equation in the context of electrochemical system when we looked at this topic in this lecture. Please look into this lecture to understand the meaning of these terms. So here, what we are specifying is the rate of change of concentration in a volume element. It changes because of two reasons. One is there is a difference in fluxes, incoming fluxes and outgoing fluxes, that is indicated by this term. And then there is a generation term. Here R refers to reaction rate. There is a volumetric generation term or a disappearance term. So these two combine to give rise to this particular term. So this is elaborated in this lecture. We want to generalize this term in the context of porous electrode. So we do this in two ways. First, we specify the amount of species I in a control volume of the porous electrode. So when we say control volume of the porous electrode, this control volume has both the electronically conducting solid phase as well as the ionically conducting liquid phase. So this is a volume element which is averaged over the solid and the liquid phase. And the amount of species present in this control volume of the porous electrode is specified by two terms. One is Ci, another is epsilon. So this epsilon refers to the volume fraction of the electrolyte present in the entire porous electrode. So the electrolyte is present in the liquid phase, and the porous electrode contains both the solid phase, the electronically conducting solid phase, and the ionically conducting liquid phase. The liquid phase component is specified by this term epsilon. And Ci refers to the concentration of the electrolyte only in the liquid phase. So the moles of species I divided by the volume of the electrolyte gives you the concentration of the electrolyte. So this multiplied by this gives you the amount of species I in the control volume of the entire porous electrode. Okay, so this term goes into this term. Okay, so when we move to porous electrode, we substitute this term into this Ci and to get this term. So this is the rate of change of species I in the control volume of the porous electrode. And it changes because of two terms. One is the superficial molar flux. So whenever we say molar flux, we are normalizing with respect to some area element. Note in this case, the area element we are considering is the superficial area, which we have specified, clarified using a schematic in the previous lecture. Please refer to that. And then here, the generation rate term also is related to the superficial volume. So all the three terms are related to the superficial terms associated with the porous electrode. Note that this term is not normalized to the superficial area. So only this term refers to a flux normalized to the superficial area. So we connect these two quantities via this important quantity A. So moving on. So we have already specified how to think about reaction rates in a previous lecture. So this is a lecture, 1/3 of this lecture refers to Faraday's law and how you specify the conventions associated with the reaction rate. So this is a fairly elementary lecture presented in another playlist, and please refer to that. This material that you have been exposed to in the high school, but we just elaborated the specific conventions we use. So specifically, we are thinking about how to connect the current densities to reaction rates. So here Jn is positive when the relevant species is product of an anodic reaction. For this case, Si will be negative. So that negative quantity with this negative sign would give you a positive quantity here. So please refer to this lecture to understand these notations. So what is important here is we have a reaction rate which is in terms of a superficial volume element that is connected to the reaction rate that is normalized to actual interfacial area, and this connection is made via this particular quantity as elaborated in the previous lecture. So the overall species balance equation is specified in the following manner. So this refers to the rate of change of species in the volume element of the porous electrode. This is a flux normalized to the superficial area. This is the generation term. So this is connected to difference in fluxes. Again, this current density is normalized to superficial area. So that connection we made in the previous lecture. So this is the overall species balance equation. So what do we have here? So we have n plus 2 unknowns. Why is that? We have n unknowns, each unknown related to species I, and we have two unknowns connected with potential. One potential connected with the solid phase and another potential connected with the liquid phase. So to obtain these two, all these unknowns, there is two potential unknowns and n unknowns associated with n species I. we have two conservation equations related to charge current balance equation, which we elaborated in the previous lecture. And we have n-1 independent species balance equation. Like this is one species balance equation. We have n-1 independent species balance equation. And then we have an electron neutrality equation. So this gives you n plus 2 equations for obtaining n plus 2 unknowns. So this completes the specification of equations to get the n plus 2 unknowns. So to get a understanding of electroneutrality equation, we have covered this in a previous lecture. Please look into this lecture if you do not remember what we exactly mean by the mathematical expression for electroneutrality condition. So the last part is how to specify the Nernst-Planck's equation for the porous electrode. So the general introduction to Nernst-Planck equation has been provided in a previous lecture. So that contains three terms associated with the diffusive flux, the migratory flux, and the convective flux. So the overall flux is decomposed into three different terms associated with diffusion, migration, and convection. So all we are doing here is how to specify the fluxes in the context of porous electrode. Notice that we have this term epsilon, which refers to the amount of electrolyte present in the porous electrode. That multiplied by Ci, Ci is specified as the concentration in the electrolytic phase. Okay, so this times this gives you the overall concentration in the porous electrode. Notice that this epsilon comes in all three terms: the term associated with diffusion, term associated with migration, and the term associated with the convection. Note this V, which is the velocity term, this is the molar average velocity in the pores. So in many a times, net velocity might not be present, but in some cases, it will be present. We'll look into that in some forthcoming lectures. So this velocity term refers to the velocity in the pores. This is the molar average velocity in the pores. In the next lecture, we will look at structural characterization of the porous electrode. With this, we conclude the third lecture, all associated with conservation laws, two charge conservation equations, and the remaining conservation equations associated with material balance. Thank you.